Okay, so you might have noticed a pattern in the last video where we looked at the derivative of a constant, the derivative of a linear function, and the derivative of a quadratic function. The derivative of all of those functions, in the first case, the derivative was zero because a constant function has a zero slope. And in the other two, what you could see was that the derivative of any function is one order less than the function itself. So we looked at the derivative of a linear function, which had an order of one and the derivative was a constant, an order of zero. When we looked at a quadratic function, which had an order of two, the derivative of that was linear, which had an order of one. And so we're going to generalize that rule right now. We're not going to prove it. It's actually proven in Appendix A4 of Quick Calculus. So if you want to review that derivation, it actually uses something called the binomial theorem, which is pretty cool, to derive this more generally. And to derive it, it always does what we always do. It goes back to the formal definition of the derivative as a limit of a rise over run taken over an infinitely small interval. Okay, so let's look at the three functions that we were dealing with before. We had s of t equals a constant. Let's call it k, okay? Then we had s of t equals kt. So we had a linear function, and then we had s of t equals kt squared. Those are three different functions where k in all cases was a constant. And we saw here that the derivative ds dt was 0. Here we saw that the derivative ds dt was equal to k. And here we saw that ds dt was equal to 2kt. And if you remember, k was 5 in the original example. When we differentiated it, we got 10. And so that's consistent with that. In general, if I have a function s of t equals k times t to the nth power, the rule for differentiating a power function is you multiply by the constant, which jumps down in front, and then you reduce the power by 1. So ds dt, which again is proven here in quick calculus if you're interested, is equal to nk t to the n minus 1. So let's apply that and see what happened over here. So for a constant, we already had a power of 0. So when n jumps down in front, it's going to multiply by 0. That gives us a derivative of 0. For kt, d by ds, d by dt of kt, we're going to first multiply by the exponent, because that's kt to the 1, times k times t to the, and now we subtract 1 from the power t to the 0, because 1 minus 1 is 0. And t to the 0 is just 1, and that's going to give us k, the original constant. So that checks off. And then finally, we have d by dt of kt squared. Well, let's use that same rule. The 2 jumps down in front, so we get 2kt, and now we reduce the power by 1, so it's t to the first, which is just t, and we get 2kt. So that also checks out. And it fits with the fact that a function changes at a rate that's one order less than the function itself for power functions. Now let's go one more step. We can look at any function now. So let's look at d by dt of kt cubed. So in that case, same rule. We're going to jump the power down in front, times k, and then times t squared. And so if we had a cubic position graph, which we could certainly have, that would happen potentially if our acceleration was actually a linear function of time. We'd wind up with a polynomial that actually had t cubed in it instead of just the familiar quadratics that we've been using for constant acceleration. And we get 3kt squared. So you would actually get a velocity that was quadratic. And you could keep going. What if you had power of fourth? You jump the 4 down, you get a cubic power. And so this power rule is really useful in physics because quite often you have powers that describe the behaviors of objects, and it's really helpful to be able to do these quick derivatives that come up all the time. Like I said, this class is about quick calculus. So in calculus, you'll probably prove all of these rules we're going to talk about over the next couple of days. We'll prove some of them, but not all of them. But at least I hope you can have a sort of conceptual and intuitive understanding of what they are.